All right, well, thanks, Masaki, for that introduction. And thanks also to Kyoto University for inviting me here. It's wonderful to be back in Kyoto. I've always had a great time in here, and in Japan in general. Wonderful place. So today is the first lecture. In this series, I want to sort of start from the beginning and hopefully get up to some work that I'm currently doing on quantum spin chains, where I have some ideas which seem to be orthogonal to what physicists actually do. Maybe there's a good reason for that. I'm trying to figure that out. But it's certainly one thing that work has led to is unitary representations of Thomson's group F and T, and a new way of constructing knots and links, all knots and links from these groups. So I take that as a positive indication from the mathematics that maybe my ideas, this block spin renormalization idea, is not completely stupid. That's my aim, is to get to talk about that work, which is what I find the most exciting right now. But this is a course, so I have to start at the beginning. And I realize I probably have a diverse audience. So I'm going to really start at the beginning with Hilbert Space. And so there will be quite a few people in the audience who know absolutely everything that I'm going to say, possibly better than I do. So to them I apologize, but there is one thing that you might find interesting anyway, which is to follow the way that I present it. Over my career, I have spent at least 20 years trying to explain the basics of von Neumann algebras and subfactors to diverse audiences, and I've come up with a lot of tricks. And for those of you that do know it, it will be quite useful to me and to everyone to ask some of the people who don't know it what they actually understand from my lectures. I would really appreciate any feedback on that score, because it's all very well to find what you think is a great expository trick, but whether it actually communicates something or not is unclear. Okay, so there's a lot of ground to cover. So I probably will not give too many proofs, but I will try to give examples that illustrate the theory in all cases. There's no time for even a single difficult proof. So that's the facts of life for these talks. So let me therefore start. As I said, I'm assuming almost nothing. And I want to begin by defining Hilbert space. And my notation will always be the Hilbert space itself as vector space will be written with this letter, and its inner product, which is a sesquilinear positive definite form on the Hilbert space, will be written with these pointed brackets. Okay, so what is it by definition? It's a complex vector space. And this, as I said, is a sesquilinear positive definite inner product. Whether it's linear in the first variable and antilinear in the second, or the other way around, is a matter of convention. But mathematicians and physicists generally have the opposite convention. So I will probably swap conventions. I hope that isn't too confusing. So be ready to see it either linear in this variable, antilinear that one, or the other way around. My colleague at Berkeley, Richard Borchards, once came up to me very excited in the corridor and told me he had found the reason why it had to be one way or the other, but I've forgotten what it was. So it's and the point is that it's complete. And the metric coming from the norm, and the norm of a vector psi is the square root of psi xi. So any Cauchy sequence in that norm has to converge. All right, well if you don't know what Hilbert space is, or you're totally unfamiliar with them, then that doesn't communicate very much. So let me give you some examples and non-examples. Possibly the most illuminating will be the non-examples. So the first thing is in finite dimensions. So in this course, typically these von Neumann algebras, the real interest is, of course, in infinite dimensions, but whenever you see a new notion or something, your first reaction should always be, what does it look like in finite dimensions? And then you can start to attack the more interesting infinite dimensional question. So, well, in finite dimensions, there's a very easy theorem of linear algebra that says that you can find a orthonormal basis of the Hilbert space in vectors which are orthogonal unit vectors, which means that the Hilbert space is actually, might as well be C to the n, consisting of vectors Z sub n, and the inner product of Z sub n with W sub n is sigma of Zn bar Wn. There, at least right now, the convention is that it's conjugate linear in this one and linear in that one. Okay? So that satisfies all these properties, and completeness is trivial in finite dimensions. All right, so now we've turned to infinite dimensions. And let me give two examples of non-Hilbert spaces. So first example would be C of T and T inverse. So this is polynomial, Laurent polynomials in one variable T, and you could insist that the powers of T be unit and orthogonal. Okay, and this is not a Hilbert space. And the reason is that it's not big enough. Right? That's because these vectors in here are just finite linear combinations of these basis, orthonormal basis vectors, and it's easy to see that that's not complete. All right, so here's another non-example, something that looks more complete. And so this is formal power series in the variable h. So you could, again, you could decide to make the powers of h orthogonal. And this is also, so remember, this is all power series. There's no restriction on the coefficients of the powers of h. And this is also not a Hilbert space. And this one is because it's too big. All right? So what we search for is the Goldilocks space in between, and that is precisely little l2 of the integers. So this is square integrable functions, sigma c n squared n belonging to z is less than infinity, and this is just right, and it is a Hilbert space. Basically, if you'd chosen other summations on the coefficients with non-involving sums of squares, you would be wrong also. You wouldn't get a Hilbert space. All right, so there's a theorem. Oh, by the way, until further notice, I will also assume that my Hilbert spaces are separable, which means there's a countable dense subset sense of topology. And there's a theorem that says any Hilbert space is actually equal to little l2 of z. And I'll put that in quotes. And this simply means that there is an orthonormal basis, i.e. there exists an orthonormal basis. And once you've got an orthonormal basis, then you can put it in bijection with z. This is infinite dimensional, of course, and therefore becomes little l2 of z. Okay? So these are the first few elementary facts about Hilbert space. So the theorem is that any Hilbert space is little l2 of z. So in fact, it's sort of amazing. There's only one, right? But that's sort of fake also, because that one Hilbert space up to abstract isomorphism may occur in lots and lots of different ways. And let me check that I'm not getting ahead of myself. and this is seen in a very interesting fashion in this very example, which is to say, so here, but this Hilbert space may appear very different. And the first example is sort of staring us in the face, which is the theory of Fourier series. We can think of little L2 of z, square integral functions on the integers, is actually the same as little L2 of the circle. And here I'll have notations T equals S1, and it's the circle set of all complex numbers of modulus 1. Or alternatively, it's a set of e to the I theta. Okay, well, so we all know from undergraduate courses that the Fourier series, if we take a sequence, what do I call this, Cn here, and I form sigma Cn e to the I n theta, this is a function that goes from this space to this space. These are now L2 functions on the circle, and it is a unitary. So let's introduce the term unitary. So U from one Hilbert space to another is a unitary if it's a surjective isometry. So to say that it's surjective means that it's onto, and then isometry means that it preserves the. I'll have lots more to say about unitaries later on, but in this initial definition, it just means that it's what I meant here when I said equals. Two Hilbert spaces are equal in the sense if there's a unitary from one to the other. In the Fourier transform, Fourier series, so this we call this F from L2 of Z to L2 of the circle is a unitary, or F. Okay, so on the one hand we have this model for the Hilbert space, which is little L2 of Z. In the other sense we have this model of the Hilbert space, which is capital L2 of the circle. So this is a little bit more complicated to deal with because you have this notion of measure and you have functions. The elements of this Hilbert space are functions defined up to sets of measure 0. In some sense, one of the strengths of the Fourier transform is that it allows you to deal with these equivalence classes of functions by simple sequences of honest functions. Right. Any questions at this stage? Okay, so I hope everyone now, if you're from topology or something, didn't know what a Hilbert space was, then you have some slightly better idea now. Just in passing, I'll add the important notion of weak convergence. Weak convergence. And so convergence in the Hilbert space simply obviously means convergence with respect to this metric. Okay, to a sequence of vectors converges to another one if the distance between them tends to 0. However, there's another important notion which we will see is quite significant, and that is we say psi in subsequence of vectors tends to another vector if and only if this is the definition. This is weak convergence. if the inner product of psi n with eta tends to psi eta for eta. Okay, so this is a much weaker notion of convergence. For instance, if you take L2 of z and you take Cn and you take the basis vectors, which are the functions that we would say, this will probably be a notation that I'll use, so let me epsilon n of m equals delta n m period, right? So this is the function which takes the value 1 on the integer n and 0 on the others. Then this sequence epsilon n actually tends weakly to 0. Provided n tends to infinity in any sense, this sequence will tend weakly to 0 because, you know, it's an L2 function, so the coefficients have to all tend to 0. So it tends weakly to 0, but obviously doesn't tend strongly to 0 because, you know, the strong convergence preserves the length of the vector. These are unit vectors, and they tend weakly to 0. So an important concept for Hilbert space, which is a bit different from ordinary convergence, it's a weaker notion of convergence. So a sequence, basically the idea is a sequence weakly converges just sort of disappears from sight. Okay, whereas if it weakly converges to 0 if it disappears from sight, whereas it strongly converges to 0 if it really comes into 0, every neighborhood. Okay, so the next thing, I'm working towards definition of for Neumann algebras, and for Neumann algebras are algebras of bounded operators on a Hilbert space. So we need to begin to study the notion of bounded operators. So I guess we might as well start complete generality and consider two Hilbert spaces, H and K. These are Hilbert spaces. And then an operator from H to K is simply a linear map. This doesn't need any specification, but to say that it's bounded means that it's bounded means, let's just say what that means, and that's that A, if we look at all of the unit vectors in H and we take the length of A psi, then this is less than or equal to sup of all unit vectors less than or equal to is less than infinity. Okay, and if it is less than infinity, then we call that number, if we call this K less than infinity, then K is by definition the norm of A. Right, so it's well known, so I think that I was supposed to give some exercises for students. So an exercise, first exercise will be to show that A bounded if and only if A continuous and here for continuous I can use either of these topologies, either of these notions of convergence, weak or strong. And second exercise is answer the question, do there exist operators that are not bounded? So this is a bit of a can of worms, actually. So that's something to think about a bit. Can you actually exhibit an operator from Hilbert space to another Hilbert space which is not bounded. Any questions about that? This is sort of obvious abstract nonsense of operators on Hilbert space. And so, as I said, I want to give examples, and the examples are supposed to be well chosen. But perhaps before I give any examples, there's some special kinds of operators that we're going to be interested in more than others. They're going to play a very significant role. So let me introduce them one at a time. So, sorry, we're still staying in the abstract realm, but actually the first kind of operator we already have an example of, and that's unitary. So an operator is unitary if it has, we've already defined it. Unitary operator. It's a surjective isometry. Right, now the next class I'm not going to be able to even define without introducing a structure on the bounded operators on the Hilbert space, which really goes back to the structure of Hilbert space itself, but I'm going to sort of, this is going to be one of my little skips as to not really properly explain why. So I just have a theorem to every A belonging to, piece of notation, B of H equals the set of all A, or B of HK, set of all A from H to K, which is bounded. So, given two Hilbert spaces, B of HK, this is curly K, not to be confused with this K, which was a bad choice anyway. Let me change that right away. M. So this notation, and if we're talking about if H is equal to K, then we just suppress it. So the set of all linear bounded operators from H to itself is just going to be called B of H. So given every bounded operator from H to K, there is a unique A star, which goes from K to H, such that, and it's uniquely defined by this condition, A xi eta equals xi A star eta. We have one way, there's always this adjoint going back the other way, and this sort of follows the abstract nonsense that I'm leaving out is that between any two vector spaces there's always an adjoint which goes backwards from the duals, but the thing about Hilbert space is that the dual, set of all bounded linear functions, is isomorphic to the space itself by this inner product. So that's a little theorem at the beginning of Hilbert space. Anyway, I'm sort of assuming it to prove this theorem, which is going to be of more interest to us. All right, so all of this to say that B of H is an involution. A going to A star, and it's conjugate linear. Right, so there's this very important piece of structure on Hilbert space, and we're seeing it on the algebra of bounded operators between Hilbert spaces. It's this conjugate linear involution defined by this formula, and its existence and definition doesn't actually depend on which way I'm assuming conjugate linear, whether it's in this variable or this variable. Either way, it comes out to be the same operator, and this map is conjugate linear. So A going to A star is simply conjugate linear. Right? So our reflex that we're supposed to be building up is, we have this notion first thing, if you've never seen it before, what does it mean in finite dimensions? Well, in finite dimensions, with the Hilbert space is C to the n, every linear operator has a matrix with respect to an orthonormal basis, and this operation is nothing but the conjugate transpose. Conjugate transpose. In finite dimensions. What about in infinite dimensions? It's also the conjugate transpose in infinite dimensions. But I have to be a bit more careful here. So the first thing is that any matrix A has a matrix form. Any A belonging to B of H has a matrix form, which is A Mn. And this, by definition, is A psi m psi n, where psi m is an orthonormal basis. Okay, so it's sort of obvious that any bounded operator is specified by a matrix, and the star operation is the conjugate transpose for this matrix. What's, of course, much more subtle in infinite dimensions is what matrices define bounded operators, right? That's sort of not so obvious at all. What if you give yourself an infinite matrix, when does it actually define, in the obvious way, a bounded operator on Hilbert space? Well, that sort of gets back to this sort of Goldilocks question. What matrices, the Goldilocks matrices that define bounded operators on Hilbert space? Well, that's not so clear.
Since your inner product is uses inner product, I guess you should put A right in this text.
Yeah, okay. Well, so throughout these lectures, I reserve the right to put it either way, and an ongoing exercise is to figure out which way it should be. Okay, to keep you on your toes, fix a convention from the start, and fix all of my formulae so that they're actually correct. I'll do this also when we come to groups. There's some inverses that should be one way and the other, and I will make it an exercise to make all of the formulas I write actually correct. Sort of inverses and left and right actions. Well, I'll write down what I like, and the exercise is for you to correct it if necessary. All right. So we spent quite a bit of time on this adjoint, and the main thing that I'm going to use it for is to define the next kind of operators. Well, actually, let's go back to unitaries. So the conjugate linear condition is simply that lambda, if lambda is a scalar, then lambda A star equals lambda bar A star. Conjugate linear. Linear, in the usual, in the additive sense, but when you multiply by scalars, you have to take out take the complex conjugate of the scalar. Right, so let's revisit unitaries. Well, it's fairly easy to see that, unitary is the same thing as this. We can actually say what the unitary condition is simply in terms of this nice little formula here: u star u equals u1 equals u star u. And since I'm doing this a bit out of order, I seem to be slightly spaced. Obviously, there's a definition which is beginning to be made, which is forget the second part. And now, is this right? One of the parts, I guess it's u star u equals 1. This is by definition. So, there's two notions, unitary and isometry. And remember, a unitary is a surjective isometry. And if you write it down, you'll see that this condition is exactly the one that says that it preserves the inner product. I think this is correct. Okay. Now, so all of this to get to the next very important definition, which is self-adjoint. And this is, if we're talking about B of H, the algebra, it's an algebra, obviously you can compose and add bounded operators. Self-adjoint means that A equals A star. So there's a unitary isometry self-adjoint. A equals A star. So this means I can spell it out, xi equals xi eta equals xi eta. You notice it only makes sense for operators from the Hilbert space to itself. It wouldn't, you know, you couldn't, A wouldn't make sense if it was different Hilbert space. Okay, and before I give you examples of this, let's do this very special case, and this is probably going to be the most important kind of operator in the whole of the course dealing with von Neumann algebras. Is among self-adjoint operators, there's these very special ones which we call projections. And a projection P is the condition that it's self-adjoint and is what's the word? Idempotent. When you square it, you get it back. So these conditions, self-adjoint idempotent, is extremely restrictive. And it's part of this basic structure of Hilbert space that this is the same thing as if and only if. It's the orthogonal projection onto a closed subspace. That is to say, somewhere in your Hilbert space you've got a subspace, and if you have psi here, then P of psi is the nearest point in the subspace to psi. Right? So as is often the case, you know, we have a simple formula giving the structure of the operator, and then a more verbose but perhaps more revealing sentence about what it is. With unitaries, it was some kind of generalized rotation. And for projections, it's orthogonal projection. So this means that, all right, our reflex once again, finite dimensions. What does it look like in finite dimensions? Well, a projection, according to a basis, you can take an orthonormal basis which starts with the subspace P contained in H. It starts with the basis element being in P and finishes off in the orthogonal complement. So we see that it looks like a bunch of ones and then a bunch of zeros down the diagonal. The projection looks like in infinite dimensions it's the same thing, except that there may be infinitely many ones here and infinitely many zeros there. Right, so that's, as I said, a very important kind of operator. And they can occur, oh well, let's see how they can occur in a rather more complicated form later on. Well, we'll see so many projections as we go that I don't even need to bother, I think. So those are the three most important ones. Let me add this last one, which I'll say a bit more. Partial isometry, which is somehow the union or the union of the notion of projection and unitary, and this is simply the property that UU star is a projection. Or we could sum that up, UU star squared equals UU star. So there's the box formula for it. But it's the same as lots of other ones. UU star U equals U. There's another one. Well, anyway, there's some other, this could be U star U equals U star. And, you know, I don't want to overload the poor student with exercises because there could be hundreds of them in this little beginning, but this is sort of a level of an exercise. But the point is, the structure of a partial isometry is that we draw sort of nonlinear representation of things. Here's the Hilbert space H, here's some subspace P, and a partial isometry between Hilbert spaces will take the vector here, orthogonally project it onto there, and then isometrically send it to U of P in some other Hilbert space. Okay, this is called the initial domain, and this is called the final domain of the partial isometry. So a very nice sort of geometric idea. All right, but we have to get back to self-adjoint operators, because they are, because there's this non-trivial theorem about them. So let's immediately say what they are. Remember, we have this reflex in finite dimensions. Well, in finite dimensions, there's this famous and often much used notion of diagonalization of matrices, and according to that, any self-adjoint operator in finite dimensions is diagonal with respect to some basis. So there exists a basis with respect to which the operator looks like that, with the lambda i's being real. Right, so that's good. Now we know what all self-adjoint operators look like in finite dimensions, at least with respect to the appropriate basis. And the first really non-trivial thing that we're dealing with here in this course is what happens in infinite dimensions. Is there an analog in infinite dimensions of this simple diagonalization of matrices? The answer is yes, but it's a bit of a big deal. I am, of course, going to assume that you already know most of the things about it. It's called the Spectral Theorem. So, contrary to what is taught in some physics courses, not all self-adjoint operators are diagonalizable. In fact, it's sort of rare. But there is a theorem called the Spectral Theorem, and I'm going to sum it up with some version of it, which says the following. This version has the advantage of actually being relatively easy to understand and manipulate without really understanding the proof, which is a good and a bad thing. It's bad in that, it's not really kosher to do mathematics when you don't know how to prove things, but it's good in that proof doesn't necessarily help you figuring it out in examples. This spectral decomposition is often as not by good guesswork and by following through the details of the proof. So anyway, what is it? Well, it says that given A equals A star, then we can view the Hilbert space, then H becomes isomorphic, so there's a unitary transformation to L2 of some measure space in such a way that A corresponds to multiplication by F. And this is the operator MF G. You have to unravel this notation on X equals F of X, G of X. So let's unravel this notation. G is supposed to be a function, an L2 function on X mu. F is some function, say a little bit more about what kind in a second. Then we take the multiplication operator MF takes MF of G and evaluates it on a point X simply by multiplying F of X by G of X. Sort of nasty looking formula, but what let's go to finite dimensions. What does this mean? Well, here let me forget some multiplicity subtleties. The measure space in this case would be the vector space of all the measure space would be the set from 1 to n, and the function would be the eigenvalues.
Can you say anything function.
Right, the main thing about the function f is that it's L infinity. So it's a trivial observation that if you have a bounded function, essentially bounded function, then this multiplication operator actually gives a bounded operator on the Hilbert space. It's just a trivial inequality with the integral. And f of x is real valued for all or almost all x. You can fix it up if it misses. And the norm of the A is the norm of MF. And this is another one of these interminable exercises, which is the essential supremum of f of x. Okay, so in finite dimensions, this essential supremum becomes trivial, and it's the norm of a matrix is just the largest eigenvalue in absolute value, the absolute value of the eigenvalue of largest value.
Excuse me, where the A appear?
Right, so that's a very important question. We have two things. The spectral theorem says that there are two notions that are equivalent. One is a self-adjoint operator on the Hilbert space, and the other is a multiplication operator from one L2 space to another. The spectral theorem says that given any A, there exists a measure space such that and a unitary operator from this Hilbert space to this one, which transports A to multiplication by F. Okay, so we want an example. And a good example is to be obtained by the Fourier coefficients, and I seem to be blanking on how exactly to do that. But yeah, so we should do that though. E.g. if you have no, that's too complicated to start with. It's sort of a bit tricky to get an example right away because the example I want to give you is a multiplication operator on an L2 space. Okay, where the spectral theorem is rather trivial because it's just the statement that the operator exists. So let me put that off as a debt to give you a nice example using Fourier Transform of how no, let's do it right away. The thing is, I'm going to do it in reverse. For some reason, that's the way I prepared this, is to do it in reverse. Example. So what I'm going to do is I'm going to sort of, this is a pretty crazy thing to do, but I'm going to start off with an operator which is already diagonalized. We already have its spectral decomposition, and then I'm going to convert it to a more complicated operator on a different Hilbert space. So let's take L2 of t, and let's take MF to be we're going to take some f belonging to L infinity of S1 T R. I'm going to take MF. Okay, so that's a perfectly fine operator which is beautifully diagonalized on L2 of T. And now I'm going to complicate it by taking the Fourier transform. And the fact of life is that f MF F inverse. So I have the Fourier transform, and I remind you that that goes from L2 of z to capital L2 of t. So F inverse goes the other way. So this gives me an operator which goes from, should go from, whoops, I think I need this. This should go from L2 of z back to L2 of z. It's just I've taken this operator and I've transported it back to little L2 of z using the Fourier series. And the answer here is, this is the first result in the Fourier series. This is the operator of convolution by the Fourier series of F itself, possibly up to some complex conjugates and minus signs. This is morally what it is. Okay? So to see this as an example of the spectral theorem, and it's a very important example, we could just say that if someone gave you the operator of convolution on little L2 of n, then its spectral decomposition would be multiplication by the Fourier series given by that sequence. Okay. And slightly more advanced, if you took, instead of taking L2 of the circle, if you took L2 of the real line, then this is also a thing, except that we'll be talking about Fourier series rather than Fourier transform rather than Fourier series. Okay, so that's certainly, well, it's a bit of a different world which we have to come to in a second. All right. So there we are up to, yeah, sure.
In what sense does this formulation help you to get information about the spectral eigenvalue distribution?
Right. So for that, I guess I haven't really prepared this, but let me say it quickly. Operators in general on Hilbert space, even self-adjoint operators, don't have any eigenvalues, but they do have spectrum, and the spectrum of any operator of A, well, let's use X belonging to B of H, is by definition the set of all lambda belonging to C such that X minus lambda times the identity is not invertible. So obviously if you have an eigenvalue, then there's no way that this, there's something in the kernel, so it's not invertible. But in general, infinite dimensions, being not invertible is much more subtle than just having an eigenvalue. And you can see that immediately by these L infinity functions. For instance, if you took multiplication by X on L2 of 0, 1, this actually has no eigenvalues. An eigenvalue would have to be a sort of point mass at some point, and they just don't exist in L2 of 0, 1. But it is true that this mx minus x, mx, the operator mx minus z times the identity for z belonging to 0, 1, is not invertible. Okay, even though there's no eigenfunction, it's not invertible. So this is the spectrum, and in general, the spectrum, this is called the spectrum sigma of x. And in general, the set of all, the spectrum of multiplication by f is the set of all essential values of f. Since everything's defined up to sets of measure 0, there's some values that you can sort of throw away, but there's some values that keep on coming back at you. Even if you try to throw them away, and that's the essential values, and it's the spectrum of M of F. Good if you like to find the essential values as being the spectrum of the multiplication operator. Okay, once again, in finite dimensions, everything is very simple. It's just, the spectrum is just these eigenvalues. Does that answer the question? Okay. Up to questions of multiplicity, you can realize that x mu as being the spectrum of the operator with some special measure on it. But that's more detail on the spectral theorem than I want to go into, probably more than we'll need, of course. Although nowhere near enough if you want to work on the subject. All right. I'm going to stop and have a 15-minute break after the hour, okay? I'm not doing very well. I have a total of 45 bullet points to cover in this lecture, so I'm up to 10. So we're not doing very well in terms of time. That's a problem I'm going to have to solve somehow. I have to say I expected it. I wasn't so optimistic that I thought that I could get through all this stuff at this level, at this speed. But now I want to have possibly the most important words so far are the connection with physics. So this is what every mathematician should know about quantum mechanics. Okay. Should probably know a lot more, but at least this basic stuff. And it sort of motivates the entire study of von Neumann algebras, and it was certainly one of von Neumann's main motivations for introducing von Neumann algebras, connection with physics. So the idea is that for very fundamental reasons, almost philosophical reasons, if you have a quantum system, the idea is that a state, whatever that means, of the system is a unit vector in some Hilbert space. Now, I need to say a lot more about the statement, in some sense what I mean by state, and indeed I'm really talking about what are called pure states, and I don't really mean a unit vector, I mean a one-dimensional subspace. A one-dimensional subspace is going to be defined by a unit vector up to a phase, right? And this is one of the main sources of confusion and lack of understanding by anyone about quantum mechanics. Some people understand it better than others, but this ambiguity of states represented by vectors up to a phase can be very confusing, right? So without telling you what a state is, except for some intuitive notion that you might have, system is in a state if it is what it is. Let me say that the second part of the correspondence is observables. So if you have a state of the system, so to be immodest the whole universe, to be more modest maybe an electron somewhere, then you can try to observe certain things on that system, such as the position where the electron is, what its charge is, how fast it's going, and so on. And the idea is, once again, for fundamental, almost philosophical reasons given to us by the founders of the subject and sort of verified by experiment to most amazing precision, observables in the system are given by self-adjoint operators. I'm going to have to say more about this later, but I will. So self-adjoint operators on the Hilbert space, so this is, we all know what they are, and they have a spectral decomposition, A, so this is charge or something, spin or something like that, and that's, under that spectral decomposition, the Hilbert space will be L2 space of some measure space, the measure space might as well more or less be the spectrum of that operator. So make it be the spectrum of that operator. I'm simplifying multiplicity questions here. So it's some L2 space. The spectrum of A is the values of the observable. So when you actually make a measurement, say of spin, you might get a number 25.5 or something like that. Well, the set of all possible values that you might get is called the spectrum of the operator. And the elements of this Hilbert space, this is the Hilbert space of states of the system. The elements of the Hilbert space are called wave functions. And here we go with the thing that ties it all together is this magic formula, which is A psi psi. So if this is an observable, and this is a state, pure state, whatever that means. A bit more about it will be revealed when I say what this is. So this is a purely mathematical thing. We have a Hilbert space. We have a unit vector in it. This number A psi psi, first observation is it's defined on the state, not just on the vector, because if you change this if you change psi by a number of modulus 1, you get the same number. Okay? It's a real, because this is self-adjoint. You can bring this over here, and by complex conjugate, you get a real number. And what it is, and as I said, this is the magic words that tie everything together, make some sense of the words state and observable, and it's the average value of the observation of observing if the system, I haven't said what that is either, is prepared in the state psi, in the state. So the sort of idealistic thought experiment is to imagine a physicist in his lab and he's looking at a meter and he's preparing the system and then he's observing something using some piece of apparatus, and every time he prepares the system he'll get some number which gives the value of, say, where the particle is, what its spin is. And in quantum mechanics this is not a deterministic thing. He doesn't always get the same thing, but if he does it again and again, sets up the system in the same state, prepares everything in exactly the same way, then this number is the average value that he's going to get after repeated measurements of the observable A. Okay, so this is what ties it all together. This shows that Hilbert space, is the essential mathematical ingredient for studying quantum mechanics, and this gives us sort of the beginning of a dictionary. This is a mathematically precise formula, and this is a whole lot of vague, imprecise words, but this sentence here, being the average value of observing A, is the thing that allows you to make a bit of sense of what a state is, what a system is, what an observable is, and how this correspondence goes between Hilbert space. Lots of good books on the subject. One of them written by von Neumann himself. It goes into a lot of more detail than what I just said. Particular projections play a role, and of course we have the spectral theorem playing a magnificent role in the center of this structure. So if you, for instance, took this, we all know there's this duality between position and momentum, and that duality is completely explained mathematically by saying that you have L2 space. If you take the position as being the observable, you get one L2 space. If you take momentum as being the observable, you get another one. And it's actually the Fourier Transform that goes in between these two. Hilbert space, well, it's the same Hilbert space, but it's realized a different spectral decomposition. Okay, so you can have wave functions in momentum space, wave functions in position space, representing the same physical system. It's just the spectral theorem applied to different operators. Okay, so I'll stop there with certainly a full 15 minutes of break, and then we'll come back. What I think the next topic on the list, yes, is unbounded operators. And since I've said that you can't actually exhibit them, there's obviously some kind of clash that's going to occur right at the start of the second part of the lectures. Okay, thanks. Going again. 2-hour lecture is a long time. It's long for me too. I'm not even sure I'll make it till the end. But, so just to ease back into the area, just to get our minds back in the same game, let me tell you about a very nice structural theorem which ties up all of these kinds of operators that I was talking about, and that's the so-called polar decomposition. So we all know that if you have a complex number, the polar decomposition, we just write it as a phase times its absolute value. Well, there's a completely analogous theorem for operators, which is the so-called polar decomposition, which says that we take any operator, this is any element in B of H. In fact, it can be in any element from one Hilbert space to another, and it has a unique decomposition as a phase, whatever that means, and I'll explain in a second, times an absolute value, and I have to explain what that means. Well, the point is, what about the absolute value? If you take A, a linear operator between two Hilbert spaces, and you take A star A, then this is sort of tautologically self-adjoint, right? This is equals A star A. And it's also tautologically, the spectrum is positive. The spectrum of A star A is contained in plus. That's, you can prove, I mean, you know, it has to be that way, right? By intimidation, if that's not true, then mathematics falls apart. So it's certainly true, you can also prove it without much difficulty. So therefore, by the spectral theorem, you can take a square root. The main function of the spectral theorem is to actually take functions of operators, because if you realize an operator as a multiplication operator by f, and you have some function that you can take of f, and you take multiplication by that function of f, and that gives you, allows you to take any kind of, all sorts of functions of operators. In particular, the simplest one, and perhaps the most useful one of all, is simply the square root of a positive function. So this is the absolute value of a. And then, once you've done that, it's a simple exercise to discover that there is a unique partial isometry. U is a partial isometry. It was a partial isometry, and it goes, remember, partial isometries are just, they project onto a subspace and take it isometrically onto another subspace. And this one takes the image of the absolute value of A, takes the closure of that, and sends it isometrically onto, the image of A, right. So once again, it takes the image of the absolute value of A and sends it isometrically onto the image of A, and you have to take closures in order to get Hilbert spaces. And those words, if you just write them down, allow you to prove this partial decomposition tautologically. There's really only one U that fits the bill. You know exactly what it has to do, or exactly where. So this is a unique decomposition. It's unique with respect to U being a partial isometry whose initial domain is the image of the absolute value, or whose final domain is the image of A, or whatever. Okay, so infinite dimensions, this is a non-trivial and useful theorem, known under a name, or probably several different names for decomposition of matrices. I can't think of any of them right now. Maybe someone in the audience knows what this means. When you write a matrix as a partial isometry times a positive matrix. The eigenvalues of the absolute value of A are called the singular, that's the singular value decomposition. This is the singular value decomposition of the matrix. Right. Now, as I promised, we're going to talk about unbounded operators. So as I said in the beginning, it's a real challenge to find an unbounded operator from one Hilbert space to another one that's not continuous. And it's somehow not of all that much interest to the subject. Well, let me be honest and say that if you take the appropriate axioms of set theory, it follows that every operator between Hilbert spaces is bounded. So what else am I talking about? This is supposed to be useful and versatile, and not depend obviously on set theory. So it's not the same notion, that's the point. What I mean by, what a Hilbert space person means by an unbounded operator is not an operator that's defined everywhere. So an unbounded operator is going to be, it's going to be an A, and it's going to be a linear operator from, but not from one Hilbert space to another, but from a subspace of the domain, which is some subspace of Hilbert space to some other Hilbert space. So it doesn't have to be defined everywhere. That's what allows it to be unbounded and both unbounded and interesting at the same time. Okay, so that's the definition of an unbounded operator. It's simply defined by, as a and to avoid trivialities, let's suppose that the domain of A is dense. Dense subspace. Right, so if you want to get examples, we have them immediately. We have two ones that we're going to deal with immediately. So example one, remember that we have L2 of a measure space. And we said that if you have a bounded function, you can define a multiplication by an operator. That's obvious. But if you have an unbounded operator, okay, sorry, a function that's not bounded, you can still define an operator, and it will be one of these unbounded operators. So suppose we have f, which is a measurable function. On x mu, then we can define mf from L2, now from the domain of mf to L2. And the domain is simply all functions for which it makes sense. So the domain of f is the set of all g's such that the integral of f of x, g of x squared d mu is this and that. In other words, if we try to define a multiplication operator by multiplying by f, then it spits out another L2 function. Okay? So we sort of meet these unbounded functions in the most natural way if we try to extend multiplication functions from bounded functions, from L-infinity functions, functions that are more general. So I mean, you really might have a function like this, right? In real life, right? This might be, your Hilbert space might be L2 of the unit interval, and you might have this function, like 1 over x. And you might say, well, I really want to consider this as something to do with Hilbert space, as an operator on Hilbert space. Well, you can, but it has to have, you just have to restrict its domain. Another example is ddx from L2 of R to L2 of R. So now you see I'm doing something which is really not allowed. I'm saying there's an operator from all of L2. Well, it's not, because not all L2 functions are differentiable. So, but I might, this would be an abusive notation, and the actual meaning of this formula would be ddx, and the domain would be all functions that are first of all differentiable, and second, if you differentiate them, then that's L2. Okay. So I might just, this is a shorthand for an operator whose domain is L2, differentiable functions whose image under differentiation is also L2. And the Fourier transform is the key to understanding this, because that will, Fourier transform diagonalizes differentiation and makes it multiplication. And so that rather mysterious question of what functions are differentiable and have L2 derivatives simply becomes, in Fourier, functions whose Fourier transform satisfies this condition for multiplication. Okay, so there's a nice example of mathematics in action. Spectral Theorem. What else do I have to say about unbounded operators? Right. So just to define something as an unbounded operator doesn't mean that you've nailed it in terms of Hilbert space, because it could be that even, you can define it on dense domain, but Hilbert space still doesn't see it at all. And so now there's a sort of section which is due to von Neumann about closed unbounded operators. And the idea is this, that if you have an operator A in its domain, so this is an unbounded operator, then let me just sum it up by saying this way. You can define, you want to define an operator A star, right? If you get a Hilbert space in, every time you have an operator, you better have a star. So you can talk about self-adjoint and so on. So, and the way you define this is it has to have a domain, A star. And the domain of A star obviously has to be the set of all eta such that if you take, such that the following formula makes sense. So that A psi eta. Remember, the formula for the star morally is this. You've got to be able to pull this from the other side. So if you take this, and if this is a bounded linear functional of psi, okay, then by Hilbert space structure, that means that there is a vector A star such that, well, you can sort that out. So this set of all eta such that this is a bounded function of psi, and in this case if this happens to be a bounded function of psi, then by Hilbert space duality there has to be a vector A star eta such that this formula holds. A little game being played here. It takes a bit of getting used to it. It's a little bit subtle, but there's really nothing to it. You take given any unbounded operator A, you take the set of all eta such that this function here defines, it's a linear functional on the Hilbert space. If it defines a bounded linear functional, then there has to be a vector A star eta by Hilbert space duality such that that formula is true. That defines A star. So this defines A star. However, if you just give yourself any old operator defined on a dense domain, guess what? You're not going to get any etas for which this gives you a bounded linear function. Okay? You've got to be in a special situation for such things to exist, and obviously what you really want is for the domain of A star to be dense. So these are the operators that Hilbert space is going to be extremely relevant to. You can have an unbounded operator with dense domain for A star. As lots of these. So the star operation actually makes sense. And there's a very simple, very clever structure due to von Neumann. If the domain of A star is dense, then we can take the graph of A, which is the set of all A psi of A, psi, A psi, such that psi belongs to the domain of A. And this is a subspace of H plus K. Right, vector in H, vector in K. And then the graph of A, the result is that the graph of A closure of the graph of A is the graph of an operator. Actually, if and only if, called closure of A. Right, so let me say it all again. If you have an unbounded operator on the Hilbert space with a certain domain, then typically the adjoint won't be defined anywhere. Just won't be any, and I've run into this more times than I care to think about. I've wanted to study some operator and the adjoint just doesn't make sense, in which case you sort of give up. But if there happen to be vectors for which this is true, this is a bounded linear functional, and there's enough of them, in fact it's dense, then what you can do is you can close the operator A, which enlarges its domain, and you get an operator which is said to be closed. And where closed means that the graph of the operator is closed. So definition, A dA is closed if the domain of A star, if it's the graph of an operator. If graph of A so in general, given an unbounded operator A, it may or may not have a closure. If it does, you say it's pre-closed. A is pre-closed. Exists. This is to say, so there's two alternative conditions, equivalent conditions. One is that the domain of A star is dense. The other is that the closure of the graph is the graph of an operator. So what happens in practice is that you're given some, suppose you were just given, I don't know, let's go back to differentiation. Then you might say, well, let's just look at Schwartz space. Okay, Schwartz space, infinitely differentiable things vanishing rapidly at infinity, beautiful subspace of L2. But we can certainly define derivative on that. Okay, but on that space, the domain is sort of not quite big enough for it to be closed. Not big enough for it to be closed, so you want to add some more stuff. Okay, what do you have to add? Well, that might be a bit mysterious, but the point is that for that operator, it is pre-closed. The domain of the adjoint is also Schwartz space, at least contains Schwartz space, so it's densely defined. So you have a proper closed self-adjoint operator, a closed operator is the closure. Right, why the big deal about closed? And here comes some miracles due to von Neumann. So here's von Neumann miracle. Miracles. Obviously, we're going to define A equals A star for unbounded operators, means, by definition, a domain of A star, domain of A star equals domain of A. And also, and the whenever this makes sense, i.e. whenever psi and eta are both in the domain of A. So self-adjoint has to be not just this thing, this is called symmetric, but the domain of the A star has to be equal to the domain of A. Okay? So being self-adjoint for unbounded operators is a bit more than for bounded operators because this domain, right? And miracle one is that the spectral theorem works as before. So if you have a self-adjoint operator, where we mean the domain of A is equal to the domain of A star, then there exists a Hilbert space, L infinity, L2 of x mu, and there exists a function, this time not necessarily bounded, but a measurable function such that there's a unitary transformation of the Hilbert space you're given to the L2 space such that the operator becomes multiplication by F. If not necessarily bounded. Okay, so that's sort of amazing. You can prove it by reducing the unbounded case to a bounded case by some kind of transform. But this is the one that really convinces you that you're onto a good thing. Just the polar decomposition works on the nose as well. So in other words, given a general closed unbounded, this is closed unbounded operator, closed, then there exists a unique decomposition where this is a closed self-adjoint positive, well, in fact. So here's the theorem. The first miracle is that if A is a closed unbounded operator, then A star A, okay, remember this is something to be dealt with a lot of caution because A has a domain, sends vectors in the domain to other things. Well, it turns out that the domain of A is something, if you apply something in the domain of A, you end up in the domain of A star. A star A, the domain of A star A is the domain of its adjoint, and this is a self-adjoint positive operator, okay? So already, just considering this guy, and the fact that everything works out, that it just turns out that this is an honest self-adjoint operator, is in my opinion, an absolute miracle. But once it is, then you have no trouble taking its square root by the spectral theorem, and then this becomes a simple, as before, bit of a formality. Okay, so you can always do this. This is a partial isometry. And this is the square root of A star. But now in a much more subtle context, because as I said, this is closed unbounded, so you have to show A star A is actually honestly self-adjoint in order to be able to apply the spectral theorem to take its square root. Terrific. So example, now we can have a real live example, which, gets us into sort of classical stuff. If we take L2 of R, and we take IDDX. Maybe 1 over IDDX exercise. And this is, on its domain, which I've said before, is a self-adjoint operator. I want to do its polar decomposition. Okay? Well, its polar decomposition is all I want to say is that it has positive and negative spectrum, so the polar decomposition will be non-trivial. All I want to say is that this U part is the Hilbert transform. U part of polar decomposition. So obviously the way to see it is to do Fourier, to switch it into Fourier space where this becomes multiplication and where the polar decomposition is obvious. So but if you don't know what the Hilbert transform is, it's the Fourier inverse applied to the operator with multiplication by -1 and +1. Something like that. Right. So, besides the mathematical reasons for studying unbounded operators, and for me the most amazing is just this absolute miracle that A star A on the nose is a self-adjoint operator if A is closed. We need to connect it with physics, because what I said in about physics was a little bit of a lie, that observables were self-adjoint operators. Well, observables in physics typically are going to have unbounded values. If you're looking at the position of a particle and it's moving on the real line, then its position can be anywhere from -infinity to +infinity. So you have to be able to handle operators, self-adjoint operators, which have a spectrum which is infinite. Well, this is just made for the job. So physics.
So,
Yeah.
I have a question about spectral theorem.
Yeah.
In the map sending A to NA, NS,
Yeah.
algebra homomorphism?
Yeah, it is. Well, it's what it really is so if we have A in the domain of A to H, and A equals A star, then the spectral theorem says that there's a unitary from H to L2 of some measure space, such that U star is multiplication by F. F. So therefore, now you can deduce the appropriate multiplicative properties, if you like, just by factors given by this unitary.
And one more question is, that is an existence theorem, right? So is it easy to construct the map?
From the spectral theorem? So the answer is that it's an existence theorem, and I said this before, but let me say it again. Often, you obtain the spectral decomposition by a lucky guess. There's a theorem that proves that it exists, but to actually apply that theorem in practice may not be so easy. The theorem, well, first of all, with the unbounded case, the first step is to reduce it to bounded operators, because then you get rid of all of these horrible domain problems. And then you prove it for the bounded ones. And the bounded ones, the proofs always go by studying the algebra generated by that self-adjoint operator. Then you use the structure of that and so on, but it's all very abstract nonsensy. So if I just give you an operator and ask you for its spectral decomposition, well, you're a bit stuck. In finite dimensions, it's very simple, right? You just give it a matrix, say a self-adjoint matrix, you want to know its spectrum, you just figure out when the determinant of 1 lambda minus A is 0, and you're done. Well, in infinite dimensions, you have to understand things a lot better. Diagonalizing, doing the spectral theorem of a single operator might be a sequence of 5 papers in the Annals of Mathematics, right? Right now, am I at least halfway through today? Not yet. No. Right, but so I have now at least done the Hilbert Space preliminaries. So we'll be able to make great progress in knowing what we're talking about quite rapidly now. But we have all of this vocabulary. We have the vocabulary of operators, self-adjoint, unitary, partial isometries, projections. We have the spectral theorem, and we have unbounded operators and their spectral theory and the polar decomposition. All of that is now defined. So now is the time, if you're confused by something, to ask a question on any of these concepts. Because we're going to start using them as I'm turning to the board, giving you a chance to think up your questions. Right, let me ask for questions again. No questions. All right, we go on to the definition now for Neumann algebras. So now I'm going to take the same attitude as I did right at the beginning of the lecture. So assuming no one knows anything about them, just as no one was supposed to know anything about Hilbert space. But now I'm going to take it modulo the fact that we know everything about everything we've done so far, self-adjoint operators and so on. Okay, so the first thing is a definition of a von Neumann algebra. So M subset of B of H is a von Neumann algebra. Well, first of all, it's an algebra. Let me not say that because it's, it's sort of implicit. So algebra simply means I can compose and add. I can multiply and add the elements in it. You have A plus B and AB. And this is composition of operators. So the three conditions, two of which are pretty innocent. Well, one of which is really innocent. You're going to assume it's unital. Why not? Now the second one is M equals M star. This does not mean that it consists of self-adjoint operators. It means that if an A is in A is in M, A star is in M. So that condition may look innocent, but we'll see that it's very stringent, very powerful. And the third one is simply that it's closed. I have to say what I mean by this closure. This is in pointwise. It means that if you have a net, AN tends to A, if the number is A psi tends to A psi. So one of von Neumann's motivations for introducing these structures was to try to do some algebra in infinite dimensions. And obviously in infinite dimensions you're going to try to set yourself up with the best situation you can to start with. And this is pretty nice. We'll see that this is an extremely important niceness condition. And this is, you might as well assume things are closed if you want to get anywhere. So it's a natural definition. And we'll see that it ties up with physics very nicely. It's not quite clear yet. Although remember that obviously M equals M star means that self-adjoint operators, there's a very simple theorem that says X is A1 plus A. Any operator is a linear combination of two self-adjoint ones. So, this condition means that self-adjoint operators, physics that's observables, are going to be very important in the study of von Neumann algebras. All right, so now let's have examples. One example. So let me start with a non-example. Oh, sorry. Let me start with an example. This is a really trivial example. Tautologically, if you take all bounded operators, they satisfy those three conditions. It's my first theorem that I've actually proved today. All right, now, example one is a non-example. It's a very important non-example. Take the set of matrices which consist of ABC, which have 0 in the bottom left-hand corner. Okay, this is an algebra. Contains the identity. It's obviously closed because we're in finite dimensions, but it's not self-adjoint. Okay? This fails to be a phenomenon. Right. The examples of things that are von Neumann algebras are, of course, A, B, C, D, because that's the 2 by 2 matrices, and that's B of H when H is dimension 2. That's a von Neumann algebra. I'm thinking of all these things as acting on C2. And the other one is the diagonals, A, 0, 0, B. This now satisfies all the conditions together with this one. So this is a von Neumann algebra. Okay. The non-von Neumann algebra is a von Neumann algebra. Right, example 3, example 2. Now we're going to let H be infinite dimensional, and we'll take a basis. So let's take the set of all matrices. So suppose we take a basis of a Hilbert space and we take the set of all operators which are to form some matrix, but eventually everything's 0. This is an algebra. Oh, it fails to contain the identity. That's tough. Well, I said that that was an innocent condition, so let's go on. It's certainly self-adjoint. Okay, but it does not. This identity thing is sort of trivial because you can always sort of throw it in and consider the example. But what it really fails on is being closed, because obviously anyone can figure out examples of small chunks of matrices which converge to operators that are not small chunks of matrices. So this failed. This is a non-example, but for a different reason from the finite dimensional one. This is a non-example because it's not big enough. It's not closed. Right? Well, we can try to close it. Well, the first attempt to close it would be to say, well, make this basis independent. We could take all finite rank operators. So this is just operators that, with respect to some basis, look like this. That's obviously an algebra, fails to contain the identity. It's self-adjoint, but most of all, it's not big enough. It's not closed. All right. Then we can go take one step further. I'd have to use a little bit of functional analysis now, and we can look at all compact operators. Making it bigger. Compact operators are all operators which are norm limits of finite rank operators. They are operators, well, there's other ways to define them, but the point is that this is still not big enough. In fact, it doesn't contain the identity, and it's certainly not closed in the topology that I said it had to be closed in. It's closed in the norm topology on operators, not in this topology. Okay, and the only way to actually make this big enough to be a von Neumann algebra is if it's all of B of H. Right? So once again, let me go over these things by example and non-example. If you want, in finite dimensions in the 2 by 2 matrices, these things, these sort of non-self-adjoint things, are not von Neumann algebras. Nothing of our theory, we say, is going to apply to a simple algebra like this, 3-dimensional algebra of matrices. It's not in our sights. We're in Japan, it's on the moon. On the other hand, if we take the diagonal matrices, that's self-adjoint, closed, blah, 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 therefore it's a von Neumann algebra. Infinite dimensions, things not only have to be self-adjoint, but they have to be big. They have to be closed. In this topology of pointwise convergence. So if we start off trying to get a von Neumann algebra by taking all finite size matrices and closing it, then if we try to close it, we're going to end up with all of B of H, which is tautologically an example of a von Neumann algebra. Okay? Our first job is going to be to construct more interesting examples of von Neumann algebras, and we can get one rather immediately from So here we go with example 3. I'm going to state this as an exercise. So if we take L2 of x mu, well, let's make it even more concrete. L2 of our favorite t, L2 of the circle, then I claim that L infinity functions of the circle acting by Remember, if we have an L infinity function of x on the Hilbert space, the L2 function by pointwise multiplication, then I claim that this is a von Neumann algebra. And obviously there's an assertion for arbitrary measure spaces as well. Okay, so let's just check that it satisfies the axioms. Well, first of all, it's an algebra. If you add and multiply functions, that will work. It contains the identity. The constant function equal to 1 is in L infinity, and it acts obviously by the identity. It's self-adjoint, because if you take MF star, this is MF bar, that's a sort of intimidation result. If that wasn't true, then the whole world would fall apart. Finally, the fact that it's closed in pointwise convergence. Well, that's a measure theory exercise, I guess. We'll see another way of doing it, perhaps better later on. Okay, so there we've got examples of von Neumann algebras.